Alright, in today's lesson we're looking at what's known as half-life. So, if we have different nuclei, we'll have different rates. Alright, and whereas we looked at, it's a bit ugly, so let's, different nuclei, different rates of decay. And so as we know, it's to do with the balancing the protons and the neutrons in the nucleus. So different nuclei have a different balance. So therefore they're going to do at different rates. Now there's an interesting pattern that appears, and it turns out for a particular, so this is for a particular radioactive isotope. Depending on whatever that might be, then the time it takes for half of our nuclei half the nuclei to decay is the same. So, which is an interesting concept, really. So that means if I've got 10 kilograms of a particular substance, say, takes 1 day for half of that to have decayed, so 5 kilograms of it decays, so we've got 5 left, into something else. And so then that 5 kilograms, it will take 1 day until that 5 kilograms, there's only 2.5 left, which is quite interesting. So that's what's called the half-life. Alright, so the time for half of the sample to decay. Alright, so an example of that is this one here. So iodine 131 has a half-life of 8 days. So if we start over here on the left there, and we've got 40 million atoms undecayed of iodine 131, then in 8 days, which is one half-life, half of that's gone, 20 million atoms left of the iodine 131. And then in another 8 days, which is another half-life, half of that decays, so we now got 10 million left. And then in another half-life, another 8 days, half of that decays, so we now got 5 million left. So that's quite an interesting relationship. And so all radioactive decay elements work in that particular way. Now the time for the half-life may be different, but the idea that half the sample is decayed into something else is the same for all of them. So there is a formula, and the formula is this: N, how much you got left, is N naught, how much you started with, the half's related to the half-life, half of the sample, and the little n at the top is how many half-lives. So that n there is our final number of atoms, if you like. N naught is how many we started with. And this little n up here is the number of half-lives. Alright, so we can use that formula. Now, We can also substitute mass and decay rate. So we can write it as m equals m naught half to the n. So if we're talking about mass. And the other thing we can do is talk about decay rate or activity, and that would we go A equals A naught half to the n. So A is activity or decay rate. All right, and in your notes there it says that the decay rate's in a thing called becquerel, and 1 becquerel is 1 decay per second. So that's what the formulas that we can use. Now, if we were to graph it, we end up with a graph that looks like this. So at the start, we've got 100% of our sample. So after one half-life, half of that sample is decayed. So we now got 50% after one half-life. Then in another half-life, so the second half-life, that's here, 50% of that has decayed. So now 50% of that is 25% of our original sample. And then after 3 half-lives, we got half of what we had at the end of the second, and half of 12.5 is, half of 25 is 12.5. So after 3 half-lives, we've got 12.5% of what we started with. And so if we join that up with the line, you can see that red line, it curves around like a bit of a hyperbola kind of thing, or an exponential. All right. It's an exponential relationship, and there's another equation you can use that we don't need to worry about. Now, these isotopes, here's a bit of a table, and the table's in your note. All right, so there's a table of a whole bunch of different isotopes, some of them natural ones up the top here, some of them artificial ones down there. So we've got what the isotope is. In the next column we've got what sort of decay, alpha, beta, gamma. In the third column what its half-life is. So as you can see, there's here, this first one here, 0.00016 seconds, pretty short, but then you go to something like uranium-238, 4,500 million years, so something very long. So there's a huge variation in half-lives. All right, and then in the last column's just things that they are used for. All right, so just a little bit of a note, and that's under under that table in your notes. All right, so first of all, the half-life pattern we wrote large numbers of atoms. All right, so large numbers of atoms, then this half-life pattern occurs. So if you only have small numbers of atoms, like 100 or whatever, even thousands, the pattern may or may not occur. But when you've got billions and billions and billions of these atoms, then this pattern occurs. Now, an individual atom has 2 options. So it can either decay or not decay. All right. So that's each individual. So if you have billions and billions of them, some are going to get decay, some are not going to decay, and you get that pattern. But the probability of decaying of an individual atom is one half, because it either decays or it doesn't, so one out of the two is one half. So each atom has a probability of half. Then when you put billions and billions together, you get that half-life pattern that occurs. Alright, so let's have a look at some examples. Now, when we do these, we can use, the formula if we like. However, it's often easier not to worry about the formula and just kind of use a little pattern and the half-life pattern. So, in this example, we've got a radioisotope of thorium, contains that many nuclei, and the half-life's a key thing, 24 days of that thorium atom. How many will remain after 24 days? So the key thing here is 24 days is one half-life. Alright, so in one half-life, half of them are going to decay. So if we've got 8, half of 8 is 4.0 by 10 to the 12 nuclei. In part B, 48 days. 48 days is 48 is 2 times 24, so that's 2 half-lives. So 2 half-lives, well, after 1 half-life, if there was 4, half of that is 2, so there's now going to be 2 by 10 to the 12 nuclei left. And then finally, C is 96 days, and 96 days is, so 24 goes into 96 4 times, so that's 4 half-lives. So after 2 half-lives there would be 2 by 10 to the 12. After another half-life that halves to 1, and then after a 4th half-life, halves to 0.5 by 10 to the 12 nuclei. Alright, and I just noticed in the notes that I've got there, I made a mistake there on that one, so see if you can just pick out that mistake that I've made. Alright, so rather than using the formula, that's kind of, I've just used that pattern. Alright, so I've kind of done that in my head, so you can set it out in another way, again, just using the half-life pattern. And here's another example. Alrighty, strontium-82, half-life of 25 days, so that's an important bit. You started with 160. In how many days would you have 10 left? Alright, so let's have a look at how we might do that. So if we start at 160, then in one half-life that halves, and that's 80. In one half-life that halves, and that's 40. Another half-life that halves, and that's 20. And another half-life that halves again, and so there's 10. So we started with 160, we end with 10. And so when we count that up, there's 1, 2, 3, 4 half-lives. So 4 half-lives. And if each half-life is 25 days, so 4 times 25 equals 100 days. Alright, so again, just using that pattern rather than the formula. Alright, third example. Alright, so let's have a look. In 2 hours, the activity of sample falls from 240 to 30. What is the half-life of this element? Alright, so this 2 hours is for that whole process. So let's look in terms of half-life, what happens. So we start with 240. In one half-life, it's going to, half of that's 120. Another half-life, half of that's 60. Another half-life, half of that is then 30. So when we look at that, we go from 240 down to 30 in 1, 2, 3 half-lives. So 3 half-lives is, again, I just noticed I made a mistake on that one, this one as well. So 3 half-lives. So 3 half-lives is, whoops, not 6 hours, 2 hours. So 3 half-lives is 2 hours. So 1 half-life would be 2/3 of an hour. All right, if we divide both sides by, and 2/3 of an hour is 40 minutes. And so again, I just noticed I made a mistake there on that. All right. All right, one last thing in this lesson before you've got in your notes, there's a whole bunch of questions on this stuff. So there's a whole bunch in your notes and then a couple in your text. Is a thing called Decay Series. All right, so if you have something decaying, then chances are that whatever's produced is also decays. So if that's the case, you get a whole bunch, one after the other, leading down, and that's called a decay series. Now, often in a decay series, the final product needs to be stable, and lead 82 in a lot of cases is the final product. So if I have a look at this diagram, all right, so this diagram here shows you uranium-238. So we start with uranium-238 at the top here. It decays by alpha, 4.5 by 10 to the 9 years, and it becomes thorium. All right, and so then that thorium-234 is radioactive itself, so it decays via beta to protactinium, and then that decays to uranium-234, again by a beta. And so you can see that those half-lives are quite different, and then that uranium, long half-life, down to thorium, down to rhodium, radon, polonium, and so on, and then eventually after all of these decays you get down the bottom here to lead 82, 206 I should say. I didn't write that quite properly there, that did I? So it should be lead 206 in terms of your mass number. All right, and so that's decayed. So this is what's called a decay series. All right, so questions in your notes, questions in your textbook. Again, there's videos on the website there, one on the decay series of uranium-238, and also a couple on half-life and radioactivity.